Hello guys, let's continue with subtopic 4.1, basic concepts of probability. And today we're gonna go over these two concepts, which is the probability of combined or compound events. Usually these two words are used interchangeably, combined or compound events. And also the concept of independent and dependent events. This class will be highly conceptual. We're not gonna do much mathematics in the sense of calculating probabilities and so on. I want you to understand this concept and this concept as well as you can, and that's all I want. So let's see, guys. So first, I'm gonna explain to you what do I mean by getting the probability of combined or compound events. Let's consider the following random trial. We have a die and we're gonna throw it, and as we know, the sample space for this experiment is getting either 1 or 2 or 3 or 4 or 5 or 6 in the die, in the upper face of the die. So this is the sample space. It's an idea that is understood by now, I believe. Okay, and remember, these are the individual or singular or elementary outcomes of this experiment. And then once I have done that, I can define events if I want. In this case, I'm giving you 5 examples. I'm defining 5 events. Event A, the die comes even. And what outcomes comprise this event A? What singular outcomes? Well, the outcome 2, the outcome 4, the outcome 6, right? All of these outcomes are favorable to the event A. And then if I want to calculate the probability of A, then that's gonna be the favorable cases, which are 3, 1, 2, 3, over all the possible cases, which are 6. So this is the probability of A. This is pretty well understood by now. Okay, now B, the die comes odd. Pretty similar to the one before. Now the only difference is that we're changing even for odd. Understood. Event C, the die comes a prime integer. How many outcomes compose event C? The outcome 2, the outcome 3, and the outcome 5. By the way, the number 1 is not considered prime, in case you didn't know. So these three singular outcomes comprise the event C, and therefore the probability of the event C happening is also 3 over 6. Pretty well understood. Event D, the die comes a perfect square. What are the favorable events? The number 1, because that's a perfect square, and the number 4. So what is the probability of D? 2 over 6. 2 favorable cases out of 6 possible ones, that's what you get. And event E, the die comes at 3. This event is composed of just a singular outcome, and therefore the probability of E is just 1/6. Okay, perfect. So far so good. This is pretty much what we have done so far. Now, let's analyze this other idea, which by the way, I didn't include here. The analysis of disjoint and joint events. What do I mean by this? Disjoint and joint events. I'm giving you 5 events right here. And in here, I want to either write that A and B are either disjoint or joint, of course, if I know what these words mean. Disjoint events means that those events do not have common outcomes. I repeat, guys, disjoint events are events that do not share outcomes. So look at A and look at B and look at the individual outcomes that compose each of these events. They clearly don't share any outcomes. You see, all of these are even, all of these are odd. They don't overlap anywhere. They don't share any particular outcome, and so we say that these are disjoint. Let me write in capital letters. A and B are disjoint events. Disjoint. And the way we can graph that in a Venn diagram, or in the way in which we can represent that visually, is this way. If this is the sample space, and if this is A, the event A, then the event B has to be over here, and they don't overlap. This event and this event do not overlap because they do not share common outcomes. Okay, now what about A and C? This is A, these are the outcomes of A, this is C, these are the outcomes of C, and I ask myself, do they share at least one outcome? This and this. Yeah, right, they share the outcome too. So we say that A and C are joint events. Joint events. They at least share one outcome. And the same idea, if I want to represent that visually, if this is A, then, well, let me draw that a little larger. Let me say that this is A. And C should look something like this. Well, the placing of C should be something like this. Okay? And this area that they share in common, guys, let me shade A. Let me shade it. There you go. And now let me shade C. There you go. This area right here that they share in common is a common outcome, which in this case is the number 2. Can you see? So the number 2 is right there. It's right there, the number 2. That is a common outcome. Perfect. Now let's go over B and C are, let's look at B, let's look at C. They are joint because they share common outcomes. So again, they are joint events. And if I want to, once again, if I want to represent that visually, I should overlap B and C. And the overlap region means the common outcomes. Okay, and then D and E. Let's look at D, let's look at E. The individual outcomes, they don't share any outcomes, so they are disjoint. And once again, they should be, if I want to represent them in a Venn diagram, they should be apart. They don't overlap. Okay, perfect. So now that we have studied this part and this part, let me ask you something, guys. Notice the following. We have these events and we have calculated the probabilities of each individual event. I know the probability of A, fine, the probability of B, and so on. Now, how do we answer? How can we answer questions like this? What does this mean? The probability of A or C. How can I interpret this sentence? Well, what this means is the following, guys. This is the probability of either A or C happening. What is A? The die comes even. What is C? The die comes prime. So I can read this as the probability of the die comes even, because that's A, or the die comes prime. This is an event in itself, and this event is combined or compounded of the individual events A and C, and they are combined by the word or. So the probability that the die comes even, which is A, or that the die comes prime, which is the event C. How can I answer this question? I mean, if I know the individual probability of A and the individual probability of C, could there be a way in which I can use them in some formula or something so that I can get the result for this one? For example, could it be this, the probability of A plus the probability of C? Could it be this formula? Or could it be their multiplication? Or could it be their division? You see what I mean? So can we find some useful formulas to answer these questions in terms of the individual probabilities of these events, of the event A, C, or D, or C, and so on? You see what I mean? That's what we're trying to look for. Okay. let me just go. Let's go over this one. The probability of, no, this one, because I already touched on the or word. Now let's go over and. What is this? The probability of A and D. The probability of event A and the event D happening both at once. What is event A? The die comes even. What is event D? The die comes a perfect square. So basically this can be written as the probability of the die comes even and also a perfect square. A perfect square. So both simultaneously. Once again, can we answer this question by knowing the individual probability of A, which we have, and the individual probability of D, which we have? This is the question that we're trying to solve today, guys. Can we find useful formulas to answer this type of questions involving the probabilities of compound or combined events by the words or and in terms of the individual probabilities? That's what we want to find out. So let's see, guys. Let's consider two events A and B, and we can make this classification. Any two events A and B are either disjoint or joint events. There is no other possibility. Either they are disjoint, which means that they don't share any common outcome, or they are joint, which means they share at least some outcome. Okay, and we're gonna deduce the formulas for the combined events, for the probabilities of the combined events, either in the case of or the case of and, in the following way. First, let's take a look at the case when they are disjoint events, which is by far the simplest case. This is a difficult one. So let's look here. So let's consider a sample space for a certain experiment, and let's consider the disjoint events A and B. So, what is the probability of A or B happening? What is the probability of A or B occurring? Let's see. First, I'm giving you in here with this symbology, guys. I'm representing the same idea in here. With this symbol that looks like a U, we are representing the word or in probability. So this and this are exactly the same. All of this and all of this means the same. And this is by far the most frequent notation. So please memorize that this little symbol, which is not a U, it's not a U. It looks like a U, but it's not a U. So this is red or, the probability of A or B. Okay, what is that equal to? That is simply the sum of the probabilities, the sum of the individual probabilities, the probability of A plus the probability of B. Why is that true? How can we interpret that visually? It's rather simple. Why is this true? Remember, guys, what does, in a Venn diagram like this, what does the area of this event represent? It represents the probability, right? The area for this shape represents its probability. And the same for B. This area means the probability of A. This other area means the probability of B. So, what is the probability of either event happening, either A or B? What is the probability of that? Well, it's just basically the addition of the areas, right? It's going to be basically the probability of A, which is this, plus the probability of B. That's about it, guys. It's just the sum of the areas. You see? Okay, now, what's going to be the probability of A and B happening, given that they are disjoint events? What is the probability that both happen at the same time? At the same time. By the way, the word and, once again, is represented by this symbol. Okay? And we see that it's 0. Why is this 0? Why is it impossible for both events to happen at once? Well, because they don't share common outcomes. let's go back to the experiment of the die. Okay, in here we can define the events A and B, which is the die comes even. Let's just write even, and the event B is the die comes odd. What are the individual outcomes for each event? For even we have 2, 4, and 6, and for odd we have 1, 3, and 5. A and B are clearly disjoint. A and B are disjoint because they don't share any common outcome, and that means, guys, that if I ask for the probability of event A and event B happening at once at the same time, that's an impossibility, because we cannot have the die coming up even and odd at the same time. It's impossible, you see? And that's the same for any events that are disjoint. If they are disjoint, then the probability of one and the other happening at the same time is 0 automatically. We don't have to discuss anything. If you know that two events are disjoint, then the probability of the first one and the second one happening at the same time is 0. It's an impossibility. Okay, so that's how these two formulas work, and we have another two formulas to put into our list. Remember that we have already one of the other formulas, which is an axiom, right? The probability of event A plus the probability of its complement is equal to 1. So we have one formula, two formulas, and three formulas that we can use in any problem. Okay, now let's go to the difficult part. When A and B are joint events. Remember, joint events means that they share at least some outcomes, at least one outcome they share in common. So what is the probability of A or B? It's this formula, guys. The probability of A plus the probability of B minus the probability of the intersection, the probability of A and B, which is this little part. Why is this formula in particular? Well, because the probability of A or B happening, either one or the other, is basically all of this area. Let me shade it. All of this area, guys. All of this. It's this part and this part and this part. You see? Now the question is this: how can I calculate this area, the area of this figure, like all of this area plus this area plus this area? How can I calculate it in terms of the probability of A and in terms of the probability of B? Well, notice the following. If we add both probabilities, if I add the probability of A, which is all of this area in particular, and the probability of B, which is all of this area in particular, if I add this area plus this area, I'm counting this intersection twice. Can you see that? Add this area to this area, and what you're gonna do is basically adding this bit in here plus this bit and this bit twice, and that's why the probability of A or B has to be the sum of both minus minus one of these areas, because I already, by doing this, guys, I'm considering this area twice, so I need to discount. I need to subtract at least one of them in order to get this area, okay, without taking this 2 times. So that's basically the formula for the probability of A or B. And this one, which is much harder to understand, is this: what is the probability of A and B happening at the same time? In other words, what is the probability of this bit in here? This section in here is when A and B happen at the same time, right? All of these outcomes symbolize the case in which A happens and also B happens, because these are the outcomes that they share in between, that they share in common. So how can I calculate this only? Well, this one you're gonna have just to accept for granted. You're gonna have to take it for granted. I cannot explain why this is true. It's just the probability of A times the probability of B. Okay, for joint events, the probability of A and B, which is often represented in this way, is just the probability of A times the probability of B, only if A and B are independent events. Only in this case can we use this formula. Now, what are independent events? I'm going to explain to you in a moment, live. Basically, I want you to understand this. We can please get used to these symbols because this is the one we're going to use a lot. So erase this. Let's erase this. Let's erase this. Okay. So far, guys, we have this formula, which is, I believe, pretty well understood. In a moment, you're going to tell me whether you understand this and this. I believe they're pretty easy to understand. Also, please write them down, write the diagram, and in a moment, you're gonna tell me whether you get the idea behind these two formulas. These two are more complicated to understand at first. Okay, but of these two, this is simpler. This one is simpler than this one. So I'm gonna assume that you understand this, and this one is rather difficult to understand. If you don't understand it, that's okay. If I have time later, I can provide some explanation as for why the probability of this section only is the multiplication of A times the multiplication of B. And in a moment, I'm going to explain to you what does it mean for A and B to be independent events. I want to do that live because it's actually quite difficult concept to understand, more or less. So let me stop it right there, guys. Now we have 5 formulas, 1, 2, 3, 4, and 5, that compose our probability theory so far. So let me go there with you.